Consider the void. It begins not with a roar, but with a breath held for eternity. A silence so profound it ceases to be an absence of sound and becomes a presence, a tangible entity. This is the interstellar medium, the great ocean between the shores of stars. To call it empty is a misnomer, a failure of human perception. Within each cubic meter, a handful of atoms, hydrogen mostly, a ghost of helium, drift in lonely orbits, so sparse that the vacuum we labor to create in our finest laboratories is a tumultuously crowded city by comparison. These atoms are the cosmic detritus, the faint afterglow of creation's fury, floating in a chill so absolute it approaches the fundamental baseline of the universe, just 3 degrees above absolute zero. Yet, to our terrestrial senses, adapted to the thick broth of an atmosphere, it is a perfect, suffocating nothingness. An emptiness that stretches for light years in every direction, a 3-dimensional desert of unimaginable scale. And in this desert, a single point of light persists. It does not twinkle, for there is no atmosphere to distort its passage. It is a steady, unwavering beacon, a fusion furnace suspended in the black. This is our Sun, a G-type main sequence star, a yellow dwarf, utterly ordinary in its stellar class, one of an estimated 200 to 400 billion similar furnaces that spin in the vast pinwheel of the Milky Way galaxy. For 4.6 billion years, it has burned, a titanic reactor fusing 600 million tons of hydrogen into helium every second in its core, converting a fraction of that mass into pure energy as dictated by Einstein's eternal equation, bathing its celestial family in a constant stream of photons and solar wind. On the third rocky world from that star, a planet of water and iron shrouded in a thin veil of nitrogen and oxygen, a curious species evolved. A species born of stardust and terrestrial chemistry, which would one day lift its eyes from the mud and contemplate not just the light, but the profound, enveloping darkness between the lights. Among those countless specks of light dusting the celestial dome, one holds a particular poignant significance. It is invisible to the unaided eye, a faint red ember hidden in the southern constellation of Centaurus. Its name is Proxima Centauri. It is the closest known stellar neighbor to our Sun. The distance is a number etched into the consciousness of every dreamer of the stars. 4.24 light-years. A figure so often recited, it risks becoming a mere abstraction, a celestial zip code. But to truly comprehend this distance is to confront the first and most formidable wall the universe has erected around our cradle. It is a wall built not of stone, but of time and the very geometry of reality. Light, the universe's ultimate courier, the fastest entity in existence, travels at a velocity of 299,792,458 meters per second. At this inconceivable speed, it can circumnavigate the equator of our planet 7.5 times in the blink of an eye. And yet, for this photon, this massless packet of electromagnetic energy, the journey from Proxima Centauri to Earth is an epic voyage lasting 4 years, 3 months, and over 10 days. Consider the sunlight that warms your skin on a clear afternoon. That light left the photosphere of the Sun a little over 8 minutes ago. It is a manageable delay, a conversation with the near present. The light arriving tonight at the mirror of a telescope from Proxima Centauri, however, began its voyage when humanity's most distant ancestors were mastering the careful curation of flame, when the first stone tools were being shaped by hopeful hands. That photon has been traveling through the void since a time when the very concept of a telescope, of a wondering mind to build one, was an impossibility buried in an unfathomable future. This distance, measured in the relentless, unhurried crawl of light, is not merely a spatial separation. It is a temporal chasm. It is the fundamental condition of our cosmic existence, the size and shape of our cage. We are isolated on an island in an ocean where the very waves that connect us are delayed by years, by centuries, by millennia. Our imprisonment, however, is a gilded one. We can see out. Oh, how we can see. We have fashioned glass and metal into eyes far more sensitive than our own, with telescopes that gather the ancient, weary photons that have journeyed for eons. We have mapped the cosmos in stunning detail. We have catalogued trillions of galaxies, each a sprawling island universe containing hundreds of billions of stars, strewn like dust motes across a void that stretches for tens of billions of light years. We are archaeologists of light, reading cosmic histories written in its spectra. We witness the vibrant, chaotic stellar nurseries within clouds like the Orion Nebula, where new suns are born from collapsing gas and dust, their ignition lighting up the surrounding medium like cosmic fireworks. We observe the serene, majestic death of sun-like stars as they puff away their outer layers into beautiful, intricate planetary nebulae, leaving behind a dense, Earth-sized ember known as a white dwarf. We document the catastrophic, violent ends of massive stars in supernova explosions, events so brilliant they can outshine an entire galaxy for weeks, forging the heavy elements, the iron in our blood, the calcium in our bones, in their ferocious hearts, and scattering them into the interstellar medium. We peer into the heart of galaxies to see the ominous, dark silhouettes of supermassive black holes, monsters weighing millions to billions of times the mass of our sun, their gravity so intense that not even light can escape their grasp, revealed only by the frantic, heated glow of the accretion disks that swirl around them like water down a drain. The universe pours its grand, violent, beautiful, and tragic story into our instruments, a narrative of unimaginable scale. But it is a narrative with a profound limitation. It is a story from the past. The light from the Andromeda Galaxy, our closest large galactic neighbor, is 2.5 million years old. We see it not as it is, but as it was when humanity's ancestors were just beginning to walk upright on the African savanna. The light from the most distant galaxies shows them as infants, mere hundreds of millions of years after the Big Bang. We see, but we can only see what was. We are cosmic historians, never journalists of the present, and more crucially, we are passive observers. We listen to the universe's one-way broadcast, but we cannot answer. The light arrives, but we cannot follow it back to its source. There is an invisible, immovable wall between us and them, a barrier woven not from steel or political borders, but from the immutable fabric of space-time itself. The speed of light is the universe's ultimate speed limit, and according to a century of physics, it is unbreakable. This is not a provisional constraint, a hurdle to be overcome with better fuel or more powerful engines. It is baked into the foundational geometry of reality, a conclusion drawn inexorably from Albert Einstein's theory of special relativity, published in his Annus Mirabilis of 1905. Nothing with mass can ever reach, let alone exceed, the speed of light. To accelerate a single proton to the speed of light would require an infinite amount of energy. To go faster would shatter causality itself, allowing effects to precede their causes, creating paradoxes that would unravel the logical sequence of the cosmos. The cage, it seemed, was not only real, it had no door, no key, and the laws of physics were its immutable, unyielding bars. But what if our understanding of the problem has been confined by a subtle error in perspective? What if the challenge of interstellar travel is not fundamentally a challenge of propulsion, of pushing a vessel faster and faster through a static arena? What if, instead, the solution lies in manipulating the arena itself? If we cannot break through the bars of our cage, what if we could convince the bars to bend, to warp, to carry us along as they move? This is not mere science fiction fantasy, though it has dwelled there for generations. This is a serious question that emerges, paradoxically, from the very equations that first described and defined our cage. It is a question that leads to a profound and tantalizing loophole, a crack in the cosmic armor that suggests the universe, in its infinite and paradoxical cleverness, may have left a key hidden in plain sight within its own operating manual. To find this key, we must embark on a journey not outward toward the glittering stars, but inward into the deepest, most counterintuitive laws of physics, and backward to a singular moment of interdisciplinary inspiration, a moment where television fantasy sparked a mathematical reality. The year was 1994. In a quiet study, a theoretical physicist named Miguel Alcubierre was engaged in an act of leisure, watching an episode of Star Trek: The Next Generation. On the screen, the starship Enterprise, under the command of Captain Jean-Luc Picard, prepared to go to warp. The order was given with characteristic gravitas. Warp Factor 1. Engage. The visual effect that followed was iconic. The stars in the view screen streaked into elongated lines, stretching into luminous bolts before vanishing as the ship leapt into the distorted realm of faster-than-light travel. For most viewers, this was a narrative convenience, a necessary suspension of disbelief to tell stories across interstellar distances within a one-hour television format. It was fantasy, a dramatic flourish to be enjoyed and then dismissed. Except Alcubierre was not merely a viewer. He was a physicist specializing in the arcane and complex field of general relativity, Albert Einstein's monumental theory of gravity. His daily work involved wrestling with the intricate, non-linear mathematics of tensor calculus, equations that describe with exquisite precision how mass and energy curve the very fabric of spacetime, giving rise to the phenomenon we perceive as gravity. He knew Einstein's field equations inside and out. He understood their implications from the subtle precession of Mercury's orbit to the terrifying singularity at the heart of a black hole. And as he watched the Enterprise leap to warp, a thought occurred to him, not as a fan of the series, but as a scientist interrogating the laws of nature. What if this visual metaphor, this stretching of space, isn't pure fantasy? What if Einstein's own equations, the very foundation of our modern understanding of gravity and cosmology, don't actually forbid this kind of motion? The question was, in the context of late 20th century physics, heretical. Every student of physics learns the cardinal rule in their first course on relativity. Nothing can travel faster than light. The speed of light, denoted by the universal constant c, is 299,792,458 meters per second. Einstein's 1905 paper on special relativity demonstrated that this speed is a fundamental constant of nature. the same for all observers regardless of their relative motion. It is the cosmic speed limit for the transfer of information, energy, and causality. More crucially, special relativity established the relativistic relationship between mass, energy, and velocity. As an object with mass accelerates, its relativistic mass increases. The closer it gets to the speed of light, the more energy is required to push it just a little bit faster, with the required energy asymptotically approaching infinity as the object's velocity approaches c. To actually reach the speed of light would demand an infinite amount of energy, a physical and logical impossibility. To exceed it is not just impossible. The mathematics of special relativity simply break down, yielding nonsensical results like imaginary numbers for mass and time. This limit is not a suggestion or a technological barrier. It is an ironclad rule woven into the structure of causality. It preserves the sacred sequence of cause and effect, ensuring that no signal, no influence, no information can travel backward in time. It is the cosmic traffic law that maintains temporal order in the universe. For nearly a century, this was accepted as an absolute, inviolable truth. The dream of interstellar travel within a human lifetime seemed forever doomed, consigned to the realm of science fiction or the bleak, long-term speculations of generation ships, vast arcs carrying entire civilizations on journeys spanning millennia, where countless generations would be born, live, and die in transit. Their original mission perhaps lost to myth. The cage was sealed and the key thrown away. Alcubierre's crucial insight, however, hinged on a critical nuance in the precise language of physics. Special relativity states with unwavering certainty that nothing can move through space faster than light. That preposition, through, is everything. It implies motion within a fixed, static background of space, like a fish swimming through water, or a rocket pushing against its own exhaust. But Einstein's later and more profound theory, general relativity, published in 1915, painted a radically different and more dynamic picture of the cosmos. In general relativity, space is not a passive, immutable stage upon which the drama of matter plays out. Space and time are unified into a single, dynamic, flexible entity, spacetime. This spacetime fabric can be curved, stretched, squeezed, and twisted by the presence of mass and energy. Mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. This curvature is what we experience as gravity. The Earth does not pull on the Moon with some mysterious, invisible force acting at a distance. Rather, the mass of Earth warps the spacetime around it, creating a curvature, and the Moon simply follows the straightest possible path, a geodesic, through that curved geometry. That geodesic manifests to us as an elliptical orbit, and if spacetime can be curved, it can also move. It can expand. It can contract. Crucially, and this is the pivotal point, general relativity places no speed limit whatsoever on the expansion or contraction of space itself. The cosmic speed limit of c applies strictly to objects and information attempting to move through the spatial background. The fabric of spacetime, the substrate of reality, can stretch or shrink at any velocity. This is not a theoretical abstraction or a mathematical curiosity. It is an observable, measured fact of our universe, confirmed with extraordinary precision over the last century. We live in an expanding cosmos. Edwin Hubble's seminal observations in the 1920s revealed that distant galaxies are all receding from us, their light systematically shifted toward the longer, redder wavelengths of the spectrum, a Doppler effect for light. The farther away a galaxy is, the faster it appears to be moving away. This relationship is encoded in Hubble's law. Now, consider a galaxy at a sufficiently vast distance. The expansion of space, whose current rate is measured at approximately 70 kilometers per second per megaparsec, accumulates over vast scales. For every additional million parsecs, a parsec being about 3.26 light-years, so 1 megaparsec is 3.26 million light-years of distance. The recessional velocity increases by 70 kilometers per second. At a distance of about 14 billion light-years, that recessional velocity surpasses the speed of light. There are galaxies at the very edge of our observable universe whose light we see, yet the space between us and them is expanding so rapidly that they are, in terms of proper distance, moving away from us faster than light. Are these galaxies violating Einstein's relativity? Emphatically, no. They are not rockets hurtling through static space at superluminal speeds. They are, more or less, stationary within their local region of space, fundamental observers riding the cosmic flow. But the space itself, the fabric between their local region and ours, is stretching, increasing the physical distance between coordinate points. Imagine two ants sitting motionless on the surface of a deflated balloon. They are not walking. Now begin inflating the balloon steadily. The ants, though stationary relative to the rubber beneath their feet, are carried apart by the stretching of their substrate. The distance between them increases not because they moved, but because the landscape they inhabit expanded. This is a precise analogy for galaxies in an expanding universe. They are carried apart by the stretching of space-time itself. This phenomenon is not limited to the relatively sedate, steady-state expansion we observe today. Cosmological evidence strongly suggests the universe underwent a far more violent and exponential episode of expansion in its earliest moments. A fraction of a second after the Big Bang, a process called cosmic inflation is believed to have occurred. In an unimaginably brief interval, perhaps as short as 10 to the negative 36 seconds, the universe expanded by a factor of at least 10 to the 26. It inflated from a subatomic speck to a volume larger than our present-day observable universe. During this inflationary epoch, space expanded at a rate that dwarfs the speed of light by an incomprehensible margin, many, many orders of magnitude faster. The universe, in its fiery infancy, flagrantly violated the speed limit it would later impose on everything within it. It did so not by moving things through space faster than light, but by manipulating the stage itself, stretching the spatial fabric at a superluminal rate. The actors, the quantum fields that would later condense into particles, were carried along for the ride. It was this cosmological behavior, this loophole written into the cosmos's own history, that Miguel Alcubierre realized could be exploited on a local scale. If the universe can expand space faster than light, and if general relativity allows for the contraction of space as well, then why couldn't we, in principle, engineer a local bubble of space-time where space contracts in front of a spacecraft and expands behind it? He sat down with the tensor equations of general relativity, the same mathematical machinery used to describe black holes, gravitational waves, and the orbit of planets. He was not looking to discover a new fundamental particle or a new force of nature. He was simply looking for a specific, self-consistent solution to Einstein's equations, a specific geometry of spacetime that would facilitate this controlled local distortion. And he found it. The Alcubierre warp drive metric, as it came to be known, is a valid, if exotic, solution to Einstein's field equations. It describes a bubble of flat, normal spacetime, a kind of gravitational life raft, or a pocket of calm in a storm, inside which a spacecraft would reside. Directly ahead of this bubble, in the direction of travel, spacetime is severely compressed. Distances in front of the ship are radically shortened. 10 light-years of ordinary, undisturbed space might be compressed into a distance of 1 light-year, or 1 meter, or even less, within this warped region. Conversely, behind the bubble, spacetime is dramatically expanded. 1 light-year of ordinary space is stretched out to 10, or 100, or more. The spacecraft itself sits at the center of this bubble, in the flat region. Crucially, relative to its immediate local environment inside the bubble, the ship is not moving at all. It is at rest. There is no acceleration force pressing the crew into their seats. But the bubble itself, the boundary between the flat interior and the warped exterior, moves through the broader background spacetime. The ship is carried along like a passenger in a moving sidewalk, or more poetically, a surfer carried on the face of a wave. Consider the oceanographic analogy in greater depth. A surfer does not paddle faster than the incoming swell. They position themselves on a wave, and the wave's propagation carries them forward toward the shore. The water molecules themselves mostly move in vertical circles, returning nearly to their original position. It is the pattern of the wave, the disturbance in the water's surface, that travels horizontally. The surfer rides that traveling disturbance. The warp bubble is precisely analogous. The spacecraft does not propel itself through space faster than light. Instead, it creates or is enveloped by a moving pattern of space-time curvature, a wave in the fabric of reality. From the perspective of an external observer in flat spacetime, the bubble and the ship within it would appear to be moving at a superluminal velocity, perhaps many times faster than light. But from inside the bubble, the ship is stationary relative to its local spacetime. There is no relativistic time dilation for the crew, as they are in an inertial frame. The cosmic speed limit of light, enforced by special relativity, applies strictly to motion through space, but the bubble is a feature of space, a moving distortion in the background geometry. The mathematics of general relativity permitted it. Alcubierre published his findings in the peer-reviewed journal Classical and Quantum Gravity in 1994. The title was direct, provocative, and deliberately evocative. The warp drive, hyperfast travel within general relativity. The reaction from the broader physics community was a complex mixture of shock, deep skepticism, and intense, grudging curiosity. Here was a reputable physicist working within the formalism of the most rigorously tested and successful theory of gravity ever devised, demonstrating on paper that faster-than-light travel was not a priori forbidden by the laws of physics. It was not magic, it was a solution. This represented a seismic shift in perspective, a crack in a century-old dogma. The cage, for the first time, appeared to have a theoretical door, even if that door was buried behind a mountain of impossibilities. Of course, in theoretical physics, the discovery of a mathematical solution is a far cry from a practical engineering blueprint. It is the discovery of a potential path on a map, with the map often bearing the legend, "Here be dragons." In the case of the Alcubierre drive, the dragons were not merely formidable, they were of cosmological proportions. The primary and most famous catch involves the nature of the material required to generate and sustain the specific curvature of the warp bubble. The equations are very clear. To create the necessary compression of spacetime ahead and expansion behind, you require a very special type of material distribution surrounding the flat region. Not just any matter, but matter with what physicists formally call negative energy density, or more colloquially, exotic matter. This is the profound and perhaps ultimately insurmountable hurdle. Everything we have ever directly encountered, measured, or created in the universe, from the atoms comprising our bodies to the most distant and energetic quasars, has positive mass and positive energy density. This positive mass-energy curves space-time in the familiar, attractive manner. It creates what we visualize as gravity wells, depressions in the fabric that draw other objects inward. Drop an apple, it falls toward Earth's center of mass, rolling down the slope of Earth's gravitational well. The Sun's immense mass creates a deep well in the solar system's space-time, and the planets trace out grooves, their orbits, within that well. This attractive gravity, this curvature toward a mass, is the only kind we have ever directly observed or interacted with. Exotic matter, as stipulated by the Alcubierre metric, would possess negative energy density. Its gravitational effect within the framework of general relativity would be repulsive. Instead of creating a valley in spacetime, it would create a hill or a hump. Instead of pulling objects inward, it would push them away. If you could hold a ball made of ordinary matter near a clump of exotic matter, the ball would be repelled. It would fall upward, away from the exotic matter, as if gravity were working in reverse. It is critical to distinguish this from antimatter. Antimatter, such as positrons or antiprotons, has positive mass and energy as confirmed by experiments like those at CERN, and is expected to generate normal attractive gravitational fields, though directly measuring the gravity of antimatter remains an active experimental challenge. Exotic matter with negative energy density is something categorically different and far stranger, a substance that has never been convincingly observed in nature in any stable macroscopic form. When Alcubierre performed his initial order of magnitude calculations to estimate the amount of this exotic material required to create a warp bubble, large enough for a modest spacecraft, the result was astronomically absurd, a number designed to extinguish hope. He calculated that you would need a quantity of negative energy equivalent in magnitude to the mass of Jupiter, the largest planet in our solar system, a gas giant over 300 times more massive than Earth. You would have to find a way to convert an entire planet's worth of mass into a form of matter that might not even exist, all to propel a single ship. It was a fascinating theoretical curiosity, a clever manipulation of Einstein's equations, but as a practical proposal for interstellar travel, it was laughably impossible. The energy requirements were beyond colossal. They were effectively infinite from any conceivable engineering standpoint. The door existed, but it was buried under a mountain of exotic matter the size of a world. But the story, as is often the case in science, did not end with that first daunting calculation. A door had been identified in the blueprint of reality, and once a door is found, inquisitive minds begin to examine its hinges, its lock, its frame, looking for ways to make it operational. In 2012, nearly 2 decades after Alcubierre's seminal paper, a physicist named Harold "Sonny" White, then leading an advanced propulsion physics team at NASA's Johnson Space Center, revisited the mathematics with a fresh perspective. He and his team explored modifications to the geometry of the warp bubble itself. Alcubierre's original model envisioned a relatively simple, thin-shelled bubble, a sudden transition from flat to warped spacetime. White asked, what if the bubble had a thicker, more gradual transition region? What if the shape of the warped spacetime region was not a simple shell, but a toroidal ring? Or what if the intensity of the curvature could be oscillated over time? By tweaking these and other parameters in the metric, performing sophisticated numerical optimizations, White and his team achieved a result that sent ripples through the small community of researchers studying speculative propulsion. The mass-energy equivalent required dropped from that of a Jovian planet to something on the order of 700 kilograms, roughly the mass of a small automobile. This was a reduction by a factor of trillions upon trillions. It transformed the problem from a cosmological scale impossibility to a merely extreme but potentially conceivable engineering and materials science. The psychological and philosophical impact of this optimization cannot be overstated. It suggested that the primary barrier to a warp drive was not necessarily one of fundamental physical law, the equations still allowed it, but of material science, control, and energy density. We went from needing to dismantle a gas giant to needing to manufacture and stabilize a few hundred kilograms of a substance we have never observed. The problem had shifted domains from the philosophical "can it ever be done?" to the practical "can we find or create this material, and can we shape space-time with it?" This shift is emblematic of the entire history of human technological progress. The impossible becomes merely difficult, the difficult becomes expensive, the expensive eventually becomes routine. The moon landing was once deemed impossible. The smartphone in your pocket contains computing power that would have required a city block-sized machine a few decades ago. The optimization provided a glimmer, however faint, that the warp drive might belong to this category of challenges rather than to the category of perpetual impossibilities like perpetual motion machines. Yet, the problem of exotic matter remains profound and vexing. Do we have any evidence, any theoretical foundation to suggest that such a substance can exist, even in principle? Intriguingly, quantum mechanics, the other pillar of modern physics, offers a faint, ghostly whisper of possibility. The vacuum of space, according to quantum field theory, is not a true nothingness. It is a seething, boiling sea of activity, a quantum foam where virtual particle-antiparticle pairs spontaneously pop into existence, borrowing energy from the vacuum's zero-point field for fleeting moments dictated by the Heisenberg uncertainty principle, before annihilating and returning the energy. This ceaseless, turbulent activity endows the vacuum with a fundamental, non-zero energy density, a background hum of existence that may have profound cosmological consequences. Under certain very specific and constrained conditions, this quantum vacuum can exhibit what is known as negative energy density. The most famous and well-established demonstration of this is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948, and experimentally confirmed with increasing precision in the decades since. The setup is conceptually simple but requires exquisite control. Take two perfectly smooth, uncharged, conductive metal plates and place them infinitesimally close together in a high vacuum, parallel to each other. The gap between them is made smaller than the wavelength of most virtual particles that can flicker into existence. This creates a restriction. The types of quantum fluctuations, the virtual photons in particular, that can exist in the narrow gap between the plates are limited to those whose wavelengths fit as standing waves between the plates. Outside the plates, the vacuum allows fluctuations of all wavelengths. This imbalance in the quantum vacuum's possible states results in a net measurable pressure. The plates experience a tiny but definitive force pushing them together. The energy density of the vacuum between the plates is lower than the energy density of the free, unconfined vacuum outside. In a relative sense, the region between the plates has a negative energy density compared to the baseline. This is a genuine, laboratory-verified, peer-confirmed instance of negative energy density arising from quantum field theory. It proves that the concept is not pure mathematical fantasy or a violation of quantum principles. It is a direct, if subtle, consequence of the theory's description of the vacuum. But the scale is the monumental, perhaps insurmountable, problem. The Casimir effect produces amounts of negative energy so minuscule, measured in units like microjoules per cubic meter, over distances so tiny, nanometers to micrometers, and for such brief, fluctuating quantum moments that it seems utterly, hopelessly disconnected from the needs of a macroscopic warp drive. The warp drive, even in White's optimized model, requires maintaining hundreds of kilograms of this exotic energy density where mass and energy are equivalent via E=m², stabilized across a macroscopic structure, meters or tens of meters in size, for extended periods, hours or days. Bridging that gap in scale is a chasm of perhaps 40 or more orders of magnitude. It is the difference between the gentle pressure of a single photon and the crushing gravitational pull at the event horizon of a black hole. It is the difference between lighting a single match and recreating the sustained thermonuclear fury of the sun. Furthermore, quantum theory itself may contain built-in safeguards, cosmic censorship principles that prevent the macroscopic accumulation and sustained existence of negative energy. Concepts like the quantum interest conjecture and various energy conditions, the null, weak, dominant and strong energy conditions in general relativity suggest that while negative energy densities can exist temporarily and locally, they must always be compensated for or paid back with a larger amount of positive energy elsewhere or later in time. Nature might allow you to take out a small, short-term loan from the vacuum's energy bank, but it demands exorbitant interest and immediate repayment. These quantum constraints might represent a fundamental prohibition, a deeper law that makes the stable, large-scale, coherent, exotic matter shell of a warp bubble physically impossible, no matter how advanced our technology becomes. The door revealed by classical general relativity might be painted on the wall, an artifact that the more complete theory of quantum gravity, a theory yet to be formulated, irrevocably locks and seals. Beyond the primary and towering obstacle of exotic matter, the Alcubierre drive concept introduces a host of other daunting secondary challenges, each a universe of complexity and potential show-stopping peril in its own right. Consider the view from inside the warp bubble, a concern that moves from aesthetics to survival. Light from the stars would not arrive at the ship's windows in any recognizable form. The severe space-time curvature at the bubble's boundary would act as an extreme gravitational lens, far more powerful than that of any star or galaxy. Starlight from ahead, traveling through the severely compressed space in front of the bubble, would be blue-shifted to an extraordinary degree. What was visible light would be shifted into the ultraviolet, X-ray, and even gamma-ray portions of the spectrum. The forward view would not be a panorama of stars, but a blazing, perhaps blinding, point of hard, ionizing radiation focused directly at the ship. Conversely, starlight from behind, having to traverse the dramatically expanded space at the rear of the bubble, would be redshifted into the far infrared and radio wavelengths, stretched into long, dim smears of undetectable warmth. Navigation by traditional stellar sight or even standard astronomical instruments would be impossible. The cosmos would be distorted into an abstract, lethal painting of invisible energies. More critically, from a physics standpoint, the bubble creates a profound and absolute causality barrier. Since the bubble moves faster than light relative to the external universe, no information from outside the bubble can ever catch up to it. Once inside and under warp, the ship is utterly, completely isolated from the rest of the cosmos. You could not receive radio messages from Earth. Those radio waves, traveling at light speed, would fall ever further behind your superluminal craft. You could not send messages out. Your transmissions would be left in your superluminal wake, unable to propagate ahead of you. You are in a moving pocket of reality, a self-contained causality bubble, disconnected from the past light cone of your destination and the future light cone of your origin. Your journey must be pre-programmed with absolute, flawless precision, accounting for the proper motion of your target star system over the duration of your trip. A calculation that requires knowing your exact arrival time, which is paradoxically affected by the warp itself. There is no way to scan for hazards ahead, a rogue planet, a dust cloud, another ship, no way to change course mid-journey based on new information, no way to call for help if something goes wrong. You are flying blind through the galaxy at millions of times light speed, trusting your pre-launch calculations and the stability of the bubble with your life and the success of your mission. It is the ultimate leap of faith, with no possibility of turning back. Then there is the problem of the interstellar medium, the very sparse gas and dust the warp bubble would encounter along its path. Space is not a perfect vacuum. It contains, on average, about 1 atom of hydrogen per cubic centimeter in the local interstellar cloud, plus a thin sprinkling of heavier atoms and microscopic dust grains. Over a journey of multiple light-years, a warp bubble moving at, say, 10 times light speed would sweep up a vast quantity of this matter. These particles cannot enter the bubble. They would need to be superluminal to cross the boundary from the bubble's perspective. So theory suggests they would accumulate at the forward boundary, the region of compressed space-time. They would be trapped in the warp field, their energy increasing tremendously as they are pushed along. Calculations by researchers like Brendan McMonigal and others suggest that a ship warping to Proxima Centauri would amass a significant amount of interstellar hydrogen at its leading edge. When the warp drive is finally disengaged at the destination and space-time returns to its normal flat geometry, this accumulated matter is released in a sudden, catastrophic burst. The energy of this release would be astronomical, as the kinetic energy of the particles, which were moving at near warp speeds relative to the local rest frame, is dumped instantaneously. Estimates suggest it could be comparable to the energy of a gamma-ray burst, one of the most violently energetic electromagnetic events known in the universe since the Big Bang. Arriving anywhere near a habitable planet would unleash this pent-up energy upon it, likely sterilizing the surface and boiling away atmospheres. Your peaceful mission of exploration and first contact would become unintentionally an act of apocalyptic planetary bombardment. You would not discover life, you would erase it. There are severe stability and control concerns as well. Maintaining the precise, exquisitely tuned geometry of the exotic matter shell is a control problem of nightmarish difficulty. The configuration is likely metastable at best. Any perturbation, a fluctuation in the negative energy density, an encounter with a slightly denser patch of interstellar gas, an internal systems anomaly, could cause the bubble to oscillate, to deform, or to collapse catastrophically. A collapse would be a disaster of unimaginable proportions. The violent snapback of spacetime from its highly warped state to flat geometry would generate immense chaotic tidal forces and gravitational shear within the bubble. The ship and its crew would be subjected to forces that would tear atomic nuclei apart, releasing energy equivalent to a supernova explosion. The crew would have no warning and no chance of survival. The warp drive is not just a propulsion system, it is a contained, artificial space-time catastrophe that you must ride with perfect balance. One stumble, and the catastrophe is unleashed upon you. And we must, with solemnity, confront the profound ethical, philosophical, and existential implications that bloom from the mere possibility of such a technology. If a warp drive were ever realized, it would instantly become the most powerful engine ever conceived by intelligence, and consequently, the most powerful weapon. The mere arrival or departure of a warp-capable ship near a planet could devastate it, either intentionally by aiming the bow shock or accidentally due to an imperfectly controlled field collapse. The history of human innovation is, tragically, a chronicle of dual-use technology. Fire cooked our food and warmed our homes, but it also burned our cities. The atomic nucleus gives us clean energy in reactors, but it also gave us the terror of mutual assured destruction. Could a species like ours, with our history of conflict and expansionism, be trusted with a tool that makes every star in the galaxy a potential doorstep? Would our first contact with another civilization be an accidental, or worse, a deliberate act of cosmic-scale destruction? The warp drive does not just challenge physics. It holds up a mirror to our own nature, asking if we are mature enough to step out of our cradle without destroying the playground. Yet, for all these monumental, perhaps insurmountable obstacles, the Alcubierre warp drive represents something of inestimable value to the human spirit and the scientific endeavor, a paradigm shift in the conception of the possible. For a century, the speed of light was not just a barrier, it was a wall inscribed with the words, "Abandon hope." Alcubierre and those like Harold White, who followed, showed us it is a wall with a theoretical gate described in the universe's own mathematical language. We found the fine print in the cosmos's contract. The cosmic speed limit applies to motion through space, but space itself, the substrate, the stage, the fabric, can dance to any tempo, can stretch and shrink at any speed. The universe itself demonstrated this in the inflationary epoch and continues to demonstrate it at the cosmological horizon. We are not trying to break a universal law, We are, in a sense, trying to learn how to consciously apply a law that the cosmos uses freely and powerfully in its grandest operations. We are students trying to mimic a trick performed by nature at the beginning of time. This quest, whether it ultimately leads to a functioning starship humming in a dock or remains forever a beautiful, impossible dream, drives fundamental science forward in invaluable ways. The attempt to solve the exotic matter problem pushes the boundaries of quantum field theory, vacuum physics, and our understanding of the nature of energy conditions. It forces us to probe the deepest questions about what nothingness really is. The mathematical optimizations of the warp metric, the exploration of different space-time geometries, deepens our comprehension of general relativity itself, perhaps revealing new insights into gravitational waves or the structure of space-time around rotating black holes. The engineering challenges of controlling space-time curvature, even in theory, cross-pollinate with other advanced concepts like traversable wormholes and closed time-like curves, enriching the field of relativistic topology. The ethical dilemmas force us, as a species and a potential interstellar civilization, to consider our place in the cosmos and our responsibilities not just to ourselves, but to any other life we might encounter. Even if the warp drive remains forever in the realm of mathematical elegance, a phantom in the equations, the relentless pursuit of it illuminates dark, neglected corners of physics we might otherwise never have a reason to explore. It is a beacon that draws our curiosity into the deepest waters. We stand now on our fragile pale blue dot, a mote of dust suspended in a sunbeam, gazing up at the starry cage that is both our prison and our inspiration. Proxima Centauri is 4.24 light-years away. With our best conventional reaction-based technology, chemical rockets, ion drives, even theoretical nuclear pulse propulsion, it is a voyage of tens of thousands of years. The bars of our prison are real, forged in the furnace of the Big Bang and tempered by the laws of relativity. But we are the prisoners who have, through sheer ingenuity, managed to find the architect's original plans. We have deciphered the blueprints of reality written in the language of mathematics. We have identified a potential weakness in the design, a speculative passage written in the cursive script of curved spacetime. We may never fashion the key. The exotic matter may be a phantom, a mathematical ghost that reality refuses to materialize in any usable form. The quantum energy conditions may be absolute guardians, ensuring the door remains forever locked. The hazards of causality violation and interstellar plasma may be insurmountable. But consider the trajectory of the thought itself. We looked at the stars and saw a prison, a gulf too vast to cross. Then we looked at Einstein's equations, the very description of that prison, and within them we saw the hint of a door. That act of looking, of questioning, of refusing to accept a boundary without first testing its every seam, is the distilled essence of our humanity. We are the universe become self-aware, a fragment of the cosmos that has awakened to examine its own rules, to run its fingers along the walls of its cell, searching for exits, for seams, for meaning. Our bodies are made of star stuff. Our minds are patterns of information evolved to navigate a savanna, yet they can conceive of surfing the geometry of space-time itself. We dream of riding waves of compressed space to other suns, of looking upon alien worlds with our own eyes, not through the delayed photons of a telescope. We dream of the day when the handle turns, the door sighs open, and the infinite ocean lies before us. Or we dream of proving, definitively, that the door was only ever a shadow on the wall, a beautiful mirage in the desert of equations. Either outcome is a victory for understanding. Either way, the search itself, the relentless, hopeful, rigorous interrogation of nature, is the journey. It is the journey that defines us. And for now, in this moment of cosmic childhood, that is enough. The stars are still there, their light a promise and a taunt, waiting in the silent, velvet night. The equations are still there, their symbols a puzzle and a potential path. The dream persists. Sleep now and dream of warp drives. Sleep and let the silent cosmos fill your mind with its infinite, whispering possibilities. Let the gentle rhythm of a world orbiting a steady star lull you as beyond its thin atmosphere, the great ocean of spacetime stretches into eternity, holding its secrets close, waiting for the day when a curious child, grown wise, might learn to speak its language and ask for passage. The night is deep, and the journey of thought is long. From the quantum whisper to the cosmic shout, from the first spark of curiosity in a terrestrial mind to the far future where our descendants may gaze upon alien suns, the story is one of relentless inquiry. We are bound by laws we did not write, but we are gifted with the capacity to read them. The page before us is the universe itself, its text written in the mathematics of gravity and quantum fields. The chapter on locomotion through space is still being written, its paragraphs filled with daunting equations and glorious what-ifs. As the Earth turns and your part of the world tilts away from the sun, remember that the darkness is not an end, but a canvas. Upon it, the stars are not merely points of light, but destinations, questions, possibilities suspended in the framework of reality. The void is not empty, it is full of potential, shaped by curvature, alive with quantum possibility. And we, the temporary assemblages of stardust, granted a brief moment of consciousness, are the ones who get to ask how and why not. The cage may be real, but the dream of the key is what makes us human. That dream will outlast our individual lives, our civilizations, perhaps even our species, as long as there is a mind somewhere to look up and wonder. So rest. Let the problems of exotic matter and causality recede into the realm of dreams. For now, simply be a thinking part of the cosmos, adrift in the great dark, yet illuminated from within by the unwavering light of a question. Good night.